So this problem says, in the hangar shown on the right, the upper portion of the link ABC is 3/8 inches and the lower portions are 1/4 inches each. Then the upper and lower portions of link ABC are bonded together at B using epoxy resin. The pin at A has a diameter of 3/8 inches, while a 1/4 inch diameter is used at C. Then we're asked to determine, in part A, the shearing stress in pin A. And so over on the image on the right, we can see the hanger along with the applied load of 500 pounds, as well as the location of pin A. And so to start off, just like any other mechanics problem, we want to begin by drawing a free body diagram of the entire system, showing all of the applied and reaction forces. So I'll start off by drawing the bottom elbow link, as well as the link ABC, just like so. And then I'll go ahead and add in the pins. So of course, starting from top here, we have pin A, and then in the center of this link, we have location B, where the epoxy resin connects the link. And at the bottom, of course, we have pin C, which connects this link to link ED. And at the top right, we have pin D. And the bottom left, we have pin E. And right at pin E, of course, we have the downward force of 500 pounds. And now for a coordinate system, I'll just simply use an XY coordinate system. Alright, so now since we have this applied load of 500 pounds at point E, we're going to have reaction forces. So for example, at point B, we will expect to have a reaction force in the Y direction that opposes the 500 pounds. And since this is a pin, we technically also have a reaction force in the X direction. And then at pin A, we will also have a reaction force AY opposing the 500 pounds. But here you may notice that this is a two-force member, meaning that we essentially have a total of two forces acting on the member, one on each side of the link, because we technically also have a reaction force CY at pin C. But however, we can just simply combine these two forces into a single member force FAC, just like so. And by doing this, we can just simply ignore reaction force AY. However, I might just leave it there for now. So next, we want to, of course, add in our dimensions, especially since these are important for resolving moments. So between E and C, we have 5 inches, and then between C and D, that is 10 inches. And of course, we also have dimensions in the Y direction, but I'll go ahead and leave them out for now, while we first find our missing forces. So for example, here we want to find force FAC. So again, we want to ignore AY, so I'll just go ahead and scratch it out. And it looks like the Y here accidentally got deleted, so I'll go ahead and add it back into our coordinate system. Alright, so now we can go ahead and find this force FAC by taking moments, since we have two unknown forces in the Y direction, which prevents us from doing force balance in the Y direction. So now, where can we take our sum of moments from? Could we try E or point D? Well, point E does have the only known force in our system, so we kind of want to use that to find FAC. So hence, our best bet is to take our moments at point D, where the additional unknown forces are located. And remember, for an XY coordinate system, we take moments around the Z-axis, so we'll go ahead and add a Z-axis to our coordinate system. And as usual, I'll go ahead and choose counterclockwise as positive, but again, you can pick whichever you choose. And I'll just go ahead and change the color of this really quick. So now the sum of moments will be equal to 0 for equilibrium. And now we can start taking our moments from point D. Using the right hand rule, we go to the next force, which is force FAC, and that'll give us a clockwise moment, which is negative, since our positive direction is counterclockwise. So to the right of the equal sign, we have negative FAC times the distance between points D and A, which is 10 inches. Remember, moment is force times distance. So the moment is negative FAC times 10 inches. And now we have one last moment, which is created by the 500-pound force. So now we take our moment from point D to point E. And from the right-hand rule, this creates a counterclockwise moment, which is positive. So this will be plus the 500 pounds times the distance between points D and E, which is the 5 plus the 10 inches. So that's 15 inches. And so that completes our moment balance. And we can now simply solve for the force FAC. So we can simply add the expression FAC times 10 inches to the left side, which will of course be equal to the 500 times 15, which is 7,500 pound-inches. And then we can simply divide the 10 inches to the right side, where the inches will of course cancel out, so we'll be left with pounds as we expect. So force FAC will be equal to 7,500 divided by 10, which is 750 pounds. So we have found the force that's essentially running across member AC. And notice this force is positive, meaning that it points upwards, which basically tells us that this is a tensile force that opposes the negative 500 pounds. So now that we have drawn our free body diagram and have found force AC, we can now easily begin part A, which asks for the shearing stress in pin A. And once again, looking at the diagram, here we have pin A attached to the solid segment up on top. So let's go ahead and focus in on this pin A. I'll go ahead and draw a quick sketch here. So here we have pin A, and essentially this pin looks like a cylinder going through a hole in this rod. And now there is a force acting on this pin, which is force FAC. And as this force FAC points upwards, it is essentially a transverse force, which is of course perpendicular to our cylinder. And now if we were to add our coordinates to this cylinder, the cylinder is pointing towards us, meaning along the z-axis. And of course the vertical axis is the y-axis. So now that we have those two coordinates down, we can now move on to the shear stress, which is noted by tau. And now if you remember from the basics, stress in solid mechanics is essentially force over cross-sectional area. So similarly here, shear stress tau is equal to the shear force, which here is essentially our transverse force. These two are the same, which in this case is FAC, over, again, the cross-sectional area of the solid of interest. So here we see shear stress is equal to shear force over cross-sectional area. And keep in mind that shear force is different from normal force since it is a force that's perpendicular or transverse to the longitudinal length of a solid. And then of course here the cross-sectional area will be a circular cross-section since we have a cylinder. And for this circle, of course, we are given a diameter. And so the cross-sectional area is just basically the area of this circle, which is equal to pi by 4 times d squared, which is equivalent to pi r squared, the form we might all be more familiar with. Alright, so now that we know what shear stress is, we can now go ahead and solve for the shear stress at pin A. So we have shear stress tau. And now this symbol contains two indices, which are two particular directions that describe this shear stress. So now notice carefully that this first index will be the normal direction to the plane, which in this case is the z-axis. And then the second index is the vertical axis that acts in the direction of our transverse force or shear force, which in this case is of course y. So that is the proper way of noting down our shear stress tau. So it's tau zy at pin A is equal to FAC, which is 750 pounds, divided by the cross-sectional area of this cylinder, which again is pi over 4 times the diameter squared. And from the problem statement, the diameter at pin A is 3/8 inches. So plugging that in, this completes our shear stress equation. And we can just simply plug this into a calculator. So 750 over pi by 4 times 3/8 squared is equal to roughly 6,790.6, and that is of course psi, pounds per square inch. So hence the shear stress at pin A is roughly equal to 6,791 psi. So now we can move on to part B. Again, finding the shear stress, but at pin C. So we are now focusing on pin C, which is of course at the bottom of link ABC. But now here you want to look closely at the geometry in the given diagram, because if you look closely, you'll notice that this part of the link has essentially two plates that are bonded together at B, right? So we have one plate towards the front and then another one behind it, which looks something like this. Whereas, for example, at pin A, there's only one link. So that one was single, and we're now looking at a double. So you might be asking, why is this important? Well, if we try to redraw this pin with the two links on each end, just like so, and then if we consider the force FAC that acts on this pin, just like it was on pin A, but if we were looking at this force pointing in the downwards direction, for example, we would get two reaction forces, one on each end of the pin because of the two separate links. And essentially these will be broken up in halves because those two need to add up to the single FAC that's on top. So basically FAC gets distributed in two, meaning divided by 2. And so knowing this, if we were now to consider finding the shear stress at this pin, we again have tau zy, since the longitudinal length of the cylinder is along the z-axis, just like pin A. So shear stress tau zy at pin C is now equal to 1/2 times 750 over the cross-sectional area of this pin, which is pi over 4, times the diameter, which we are given in the problem statement, which is 1/4 inches for pin C, and that is squared. So again, looking at the pin, we will have two shearing stresses, one on each side. So hence, in this case, this is a double shear situation, since again we have two forces. So putting this expression in the calculator, we get 7,639.4. So hence, the shearing stress at pin C is roughly equal to 7,639 psi. So now in part C, we are told to find the largest normal stress in link ABC. And so now we're focusing on the entire link ABC. And this time we want to find the largest normal stress. And so how do we find the largest stress in the link? Well, first of all, we want to really understand the relationship between stress and, say, cross-sectional area of a solid. So for instance, here we want the largest stress. So we pretty much want to increase and maximize stress. And so in principle, whenever you want to increase stress, you want to decrease the area of your solid. So basically by decreasing the area, you are increasing stress. As you can see, for example, in these shear stress expressions, since stress and area are inversely proportional to one another, where area, of course, is the denominator of the expression. So now considering normal stress, let's say we have sigma zz, where in this case the first index denotes the normal direction to the plane of interest, where in this instance is in the direction of the z-axis, and the second index refers to the direction of the internal force, where in this case our normal force is expected to point in the same direction as the normal direction, hence the z direction as well. And so we know that normal stress sigma is equal to the axial load P, aka the normal force, over a cross-sectional area of our solid. And so again, here you can see how decreasing the area yields a larger stress since you are dividing by a smaller value. So now that we understand this principle, then let's go ahead and find the largest normal stress in link ABC. So going back to the picture here, let me just get rid of this. So we essentially have two different changes in area. One at pin A, where we have 3/8 inches in diameter, and then the other at the bottom, which is at pin C, where we have 1/4 inch diameter. And so of course we know that 3/8 is larger than 1/4. And so knowing this, where would we expect to have the smallest area along link ABC? Well, for instance, let's go ahead and imagine a cross-sectional view of pin A over here, where we're slicing the link horizontally. Of course, from top to bottom, we will see a cross-section something like this, where we have a hole in the center, which pin A takes up. And well, since pin A has a larger diameter, therefore it is taking up more space compared to pin C that has a smaller diameter. So we will expect the area to be smallest at pin A. And so to help visualize this here quickly, I'm just going to redraw this cross-sectional view of course, pin A. And so essentially we have a rectangular shape of link ABC as seen from top to bottom. And in the center, of course, we have pin A. And on the sides in blue, we have the actual solid portions of the link. And in red is the pin A, which is again a hole with the cylinder going through it. And the cross-sectional area of interest is in blue. And now if we were to compare it with pin C, which has a smaller diameter, we're essentially getting more blue area, right? So the cross-sectional area will be slightly larger at that location. So that is not what we want, since we want to maximize stress where area is the smallest. So now, of course, we want to have the dimensions of these walls of the link. And from the problem statement, we know that this upper portion of link ABC is 3/8 inches, and the length is given to us on the diagram, which is 1.25 inches. So hence our net area of this whole cross section, which is again at pin A, will be equal to, of course we know that area of a rectangle is simply length times width. So in this case our length is 1.25 inches, but of course we need to subtract the area that fills up pin A, which is simply the diameter of the pin, which is 3/8. And so the length here is 1.25 minus those 3/8 inches. And then of course times our width, which is simply 3/8 inches. So now that we have the area, of course we need the axial force now. And to visualize this normal stress that's created from this axial load, of course it'll be going along the normal direction to the plane, just like so. And then of course the axial load that's occurring here is force FAC, which acts along the y direction. So hence our normal stress sigma will have the indices YY, as the stress acts along the direction of the normal force, which again acts in the y direction, both along the normal direction. And so our axial load in this case is again force FAC, which is 750 pounds. So hence we can now solve for the largest normal stress, which is sigma YY equals 750 pounds over our net area, which I'll go ahead and quickly solve here. We get about 0.3281 square inches. So adding that to the denominator over here, we have 750 pounds over 0.3281 square inches, which is roughly equal to 2,285.7 pounds per square inch. So hence, our largest normal stress, sigma YY, is roughly equal to 2,286 psi. So now, last but not least, we have part D, where we want to find the average shearing stress at B. And so in the diagram, B is the location where the epoxy resin is being used to bond the link ABC together. And so now we're again looking at the shearing stress, but this time at location B. And so looking back at the diagram here, let me get rid of these previous markings. If you notice here at B, we're given a distance of 1.75. And so if I were to redraw that location for a better view, here this is the upper portion of link ABC, where pin A is located. So that right there is pin A. And then this dotted line measures the start of location B, which marks the start of the bottom portion of link ABC. And the width of this member was 1.25 inches. And so from that dotted line down to the bottom of this member is the 1.75 inches. And now in addition, let me just draw a side view of what we're looking at here to have an even better view. So that is pin A up on top. And then below that, where the members meet, is of course location B. Then internally, of course, we have the force FAC. And then at the bottom is where that force gets distributed in two, which are the 1/2 FACs that we had previously. So maybe this was a slightly better image to help visualize that double shearing effect. And so again, this portion right here between the two members is the 1.75 inches, where the dotted line on the left is this top edge right here. And so if you notice, this portion has an area which we'll call AB, and that is simply equal to 1.75 inches the length times 1.25 inches the width. And so hopefully this gives you a hint for how we're going to solve the shearing stress tau at B. And so again, shearing stress is the shear force over the cross-sectional area, where here the shearing force is essentially the 1/2 FAC, since that is the force acting at B. So we have 1/2 times 750 pounds over the area AB, which is the 1.75 times 1.25. So calculating this expression, we will get roughly 171.43, and that is of course pounds per square inch. So hence, the average shearing stress at B, tau B, is equal to 171.4 psi.